Switch it on.
That's like. Can I take water from you? Bitte?
Ich stelle mich dann rechts hin, gleich neben und gehe dann so auf die Seite, dann können Sie gleich direkt am Computer. Ne?
Okay.
Good morning, ladies and gentlemen. It's a great pleasure for me to chair one of the first sessions here at our ICMPC conference. I'm Annemarie Seiter-Preisler, member of the Institute of Systematic Musicology, so I'm a colleague of Richard. And it's a great pleasure for me to introduce our first speaker, Andreu Vall. Welcome to this presentation. He's coming from the Johannes Kepler University in Linz.
Hello, everyone. Is this fine with the sound? I think so, right? And okay, my slides are here. Okay, and can I go back? Yeah. All right. So hello, everyone. My name is Andreu Vall. I'm coming from the Institute for Computational Perception in Linz. This is joint work with Massimo Quadrana. He's working at Pandora, a popular music streaming service in the US, and with Markus Schädel and Gerhard Widmer, who are supervising my, my research in Linz. So the research I'm presenting today is framed in the context of music streaming services, where it's helpful to provide automatic recommendations to users who might need help to navigate large music catalogs. So basically, imagine that we have those 5 songs that the user is listening to. This is a listening session, and we might want to be able to automatically recommend something next. Basically, we will use some concepts here. A playlist model will be any algorithmic or computational approach that can look into those songs and can make a suggestion for later, what the user might want to listen later. We will say that the song context here in this problem is just the songs that just were played so far, and the song order, of course, will be the order in which these songs were played so far. So what we are trying to address in this research is the following questions. Is knowing those songs, what songs happened so far, and the order in which the songs happened so far important to decide what to predict next? Basically, the way we will try to answer this question will be by conducting some numerical experiments We will simulate that we extend playlists, and we will try to see if those variables, context and order, are important or not to decide what to recommend next. And we will be exploring different types of playlist models with different characteristics, and depending on the results we observe, we will be able to deduce, okay, this was important, this was maybe not so important. Because of time constraints, I will be focusing only on the discussion about the song order in next song recommendations. The song context, you can find details in the paper we contributed to the proceedings, or we can also discuss after the talk, but I would like to keep the discussion now to the song order, the importance of the song order for next song recommendations. So, as I said, this will be a numerical experiment. We need data to analyze and to learn patterns from. So we will be using databases of hand-curated music playlists. For example, what you see here is a playlist that a user of the Art of the Mix is a playlist sharing platform. This playlist was put together by a person, by a user, and shared online. We are using those playlists because those are sequences of songs that some amateur DJ took the time to put together. So there is some attention put into this list of songs, and we will use those playlists both to learn patterns using statistical models, and also to decide and to assess if our playlist models can or not predict good recommendations. And we will do the following experiment. We will use a playlist model based on a recurrent neural network. A recurrent neural network is a type of statistical model that can look at a sequence, look at the songs that happened so far, is aware of the order in which those songs happened, and can make a prediction for a song next. So it's a pretty complete model for the task we are trying to address here. And what we will do is the following. We will ask this playlist model to extend regular original playlists, like the one I just showed before. But then, on parallel, we will also ask the same playlist model to extend playlists where the order of songs has been shuffled. So basically, we are trying to fool this model. We are showing him regular playlists and ask him to predict recommendations, and we are showing playlists with shuffled order and trying to see if this is a problem, if this is a difficulty for the model or not to predict the next song. So another important thing that we need here is a way to assess if the playlist model does or does not predict good continuations for the playlist. How can we do that? So as I said, this will be a numerical experiment. We will not really be asking a user to assess if the recommendation was good or not. We are just going to keep it offline. So we will borrow an evaluation technique from the domain of session-based learning models. We will do the following. We have this playlist that I just showed you before, and we will use it to simulate a recommendation scenario. We will just show the beginning of the playlist to the playlist model and ask the model to recommend something next. The model doesn't know what comes next, but we do know what comes next. In this case, after having seen 5 songs, the next song in this playlist was Creep by Radiohead. We will ask the model to rank all the songs that could come next in order of preference. And then we will look at the following. The song that actually came next in our playlist, was the model able to identify that that was a relevant song? In this case, it was pretty able. The model ranked the songs as possible candidates according to some inner probabilities that it computed, and it saw that Creep by Radiohead was in second rank, likely to be the next song. We will keep track of this rank. Then we will show one more song to the playlist and again ask to predict ranks for the next songs. In this case, the model got it right. The song that the model thinks is most likely to be the next one is ranked in first position of preference. And we keep track of this rank 1 now, and so on. We will basically do that for the whole playlist and for many playlists. And we will do the same experiment, but where the songs that we show to the model are shuffled. Now, we will compare the results obtained by the playlist model on original playlists and on shuffled playlists. What we would like is that the model is able to really get right what the next song should be. This means that the model should be able to place always the next song in the top position or close to the top position. We would like to achieve ranks that are low. So here I'm showing you the results of the playlist model on original playlist, where nothing happened, where the playlists were just showing the original order. What you see in the x-axis is the position in the playlist for which we made a prediction. So when we have seen one song and we predict a song for position 2, when we have seen 2 songs and we make a prediction for position 3, and so on, up to position 8. And what you see in the y-axis is the ranks achieved. These boxes are box plots. Basically, they show the distribution of the achieved ranks. We would like these boxes to be as close to the bottom of the chart as possible. This would mean that the model gets it right. What we can see here is that when the playlist model sees more songs, the boxes go down and down. So the more context the playlist model has, the better. And what I would like to show you now is what happens when we shuffle the playlists. When we shuffle the playlists, the same model is showing basically similar results. If you compare the boxes on the left plot with original playlist and the right plot with shuffled playlist, the ranks achieved by the actual next songs in the continuations are pretty similar. What this plot shows us is that basically in the listening experience, the order of the songs might be important. But for this playlist model, which is pretty powerful and very complete, it's not really a difference if the songs played so far are in the right order or in any shuffled order. You can see even more experiments in the paper. So basically, to sum up, I just talked about the song order today, but in the paper you can find also experiments on the context. We have looked at the importance of the context of songs and the order of songs for next song recommendations. We've evaluated that by means of numerical experiments in which we simulated the recommendation as scenario. And in our experiments, the song order did not appear to be relevant to make good recommendations, which doesn't mean that the song order wasn't relevant in the listening experience, but not for the playlist model. And you can check more stuff in the paper, or we can talk later. Thank you. That's it.
So thank you very much for this interesting talk, and I hope that we will have a lively discussion. Yes, please.
I just didn't really fully understand. So what data did you train your model? Was it just the title and the track? Or
Yeah.
Actually the acoustic recording?
No. Yeah. So in this case, we are using 2 playlist collections, one from The Art of the Mix and another from 8 tracks. And in both cases, we're just using the names. So this is like, it's basically like language models. It's like if those were words, and we see them in sentences, and we don't know the meaning of the words, we just see which words come after which. It's how we do it here.
Yes, another question? So if there are no other, yes, please? No. If there are, I also have a question.
Mm-hmm.
So how would you avoid to create something like bubbles? So this is not specific to music, music playlists, but it's a general question in automated selection of materials. Yeah. So is this desirable? What is your opinion on that?
No, that's a very good question. So so in this paper, not so much, but in the extension of this paper, we compared this model to other similar models. And it's a common phenomenon, what you say, that popular songs keep on appearing and appearing, or the songs that the user likes keep on appearing and appearing. The way of preventing that is by either using models that are more robust to these popularity effects. That's something that we briefly discussed in the paper. Or even by introducing, as the colleague said, not just looking at the songs by their names, but by their characteristics. And in this way, it's easy to get other songs which are maybe unrelated from popularity and consumption pattern, but are related in another way. And this enables, it's pretty easy then to find long tail songs that are not very popular. Yeah.
you very much. May I ask another question?
Yeah.
So, there is this big data facility. So have there been any attempts to utilize this data, for instance, on personal information in order to facilitate the selection of such materials?
Yeah, I would say this is the whole goal of it. So this is basically the exploitation of massive amounts of data for that. So in this case, the datasets we are using here are of a moderate size, but when Spotify does that, when Pandora do that, this is basically what we are trying to do. So those models are basically gathering the information from not only my taste, but combining massive amounts of data. So this is it, yeah.
Okay, thank you very much. Are there any other questions from the audience? Yes, please.
Did you try to put the emphasis on just the last song in the playlist and not all the songs?
No.
It might be important which song comes back before the song that we're trying to record.
I'm not sure I understand. So, can you maybe repeat?
In a playlist, sometimes when DJ tries to merge the song, he just looks at the ending of the song, in which key it ended, or maybe which mood it had when it ended, and then he tries to pick the next song, which blends smoothly.
Yeah.
So maybe if you try to look at just the previous song in the playlist and some characteristics of the playlist in general, maybe there will be an effect of the order.
I'm not sure if you mean like looking at the inner of a song and seeing how the end of a song connects to the beginning of the next song, or you are talking about the last song of a playlist?
I'm talking on the last song, which you in the part of the playlist that you use to predict the next song, right? Because you don't necessarily always predict.
You start from the beginning, and you always show from the beginning up to.
Up to, yes.
Yeah.
Up to this last song, and then you, when you feed your data into your model, you take the characteristics of the playlist in general, and you add the characteristics of the last song in the chunk, in the part of the playlist preceding the song that you're trying to predict. Okay. We will talk about it later.
Okay, I couldn't understand what you mean. Yeah.
Thank you. Are there any more questions from the audience? So if not, I would like to thank you very much for this talk and introduce our next speaker. It's Olivier Lartillot from the University of Oslo in Norway. Sorry, it's our first session, so please excuse my...
Thank you. Okay. Forward. Okay. Right. That.
Yes, yes, here 1 minute. Camera. Did it move? Did it move this? Okay. It's close enough? I can move it. Yeah, because it moves. It's okay? Yeah? Just oops.
So welcome, ladies and gentlemen, to our second speaker here in our session Computing. It's Olivier Lartillot from the University of Oslo in Finland.
Norway. Norway.
Norway, excuse me. That's
I used to be in Finland before.
Yeah, sorry.
Yeah, no problem.
Embarrassing. Okay.
Thank you. I will discuss about the state of the art in computational research for detection of pitch from audio. And I will discuss in particular the interest of founding those computational models on perceptive or cognitive models of pitch detection. Unfortunately, up to now, cognitive models of pitch detection are maybe not sufficiently advanced to be useful for computational research to advance in the state of the art in computational pitch detection. But we might hope that now there are new advanced new progress in this research on cognitive modeling of pitch detection. So maybe we can take the benefit of this discussion forum to try to bring together further computational and music perception cognition expertise. Right, so just to mention, so I work also on this computational modeling of pitch detection, and in particular application for Norwegian folk music played on Hardanger fiddle. The particularity of this is that you can play more than 2 strings, 3 or 4 strings at the same time. There are also sympathetic strings below. Here is an example of what you can achieve. I can remove this. The result of the model that I have been developing for a given piece of music. We can get the notes over time. So you see the temporal location of each note and the pitch height in frequencies. I will play one example. This one. Okay, and we can get quite detailed representation of the continuous pitch modulation over time and also the amplitude modulation over time. Okay, so computational pitch detection is a part of automated transcription. So you have an audio recording and you want that the computer be able to reconstruct the score from that audio recording. But this is very difficult to reconstruct the score, so this is a simpler problem, simpler but still difficult, to reconstruct a kind of piano roll representation, so to detect the notes and to get the temporal location of each note in seconds and the pitch height in frequencies or in semitone. But even this simpler problem is quite difficult, and it remains a challenge in this community of music information retrieval. And the current results are still quite moderate, and even for simple polyphonies, we don't get that very good results. It's not very robust. It can't be used professionally for your own purposes. And so there are different approaches very quickly. One is based on a purely signal processing approach, like computing spectrogram, FFT, or autocorrelation, and then from this representation, designing some general heuristics to get to detect those pitch from these signal processing operations. Then there is a bunch of new methods that use a kind of training or learning. So some, for instance, templates, so you can get a big database of samples of single notes played on different instruments for different pitch height. And then you have your own recording, and it is automatically redecomposed into those single notes. But for instance, for our case of fiddle music, it will not work well because there is so much continuous transformation of timbre and pitch that it's not suitable for this type of approach. A very trendy approach nowadays is to use machine learning, deep learning approaches. So basically you have a neural network and you train the neural network by providing audio recordings of music and also by providing the score of these audio recordings. And then the neural network will try to learn by itself how to get the score from the recording. But for instance, in our case, that will mean that we will need to give to the machine those very detailed recordings that I showed, detailed transcription that I showed as a result of my research. And this is difficult to get this manually, so it will not make much sense in our case. Because those research are so difficult task, sometimes they try to improve the results by adding stylistic constraints based on music theory or statistical analysis. For instance, you could say after C there shouldn't be F sharp, or it's quite improbable, but it simplifies the problem, but it will restrict the range of application type of music and so on. So now that we are here in ICMPC, you might wonder, but what about trying to model the way we perceive music? Let's try to build machines that will follow the same type of rules. So how do we perceive pitch, for instance? We have the outer ear that filters the sounds, and then there is a cochlea that will perform the tonotopic decomposition of the sound into frequencies, and then the decomposition of the frequency range into critical bands, and there is a transduction of the auditory signal into a neural signal, and for each critical band you have F0 estimation performed now more in the central auditory system, and then this is conversion. There is a cross-band integration of these different F0 estimation, right? But those models, we know quite a bit about the cochlear model, for instance, but about this more central auditory system, it's still quite hypothetical. We don't know that much, not enough to create a computational model. There have been some attempts, for instance, by Encyclopedia to model the whole system. There is still the question how to perform the F0 estimation using autocorrelation, comb filter, and so on. We don't know that much, and it seems, for instance, that the critical bands decomposition distorts the signal quite a bit and is not that useful right now for the computational analysis. So it's quite telling that the same researcher, just after this model, decided to create a more engineering approach that is less using cognitive models, but using simpler heuristics, but that this new approach was now a kind of kind of state of the art. Can you hear me? No. Does it work? Should I wait? It's okay. I don't hear myself anymore. Yeah. We will fix that while we talk. Okay. Right. So it's using FFT spectrum and harmonic summation. So what is harmonic summation? So it's purely an engineering method. So for instance, you have here one pitch played. So you have the fundamental and the different harmonics. And so to detect this, you could say, okay, this is a periodic signal in the spectrum. And so we could try to detect, to sum all those amplitudes on all these harmonics. So let's consider a given frequency candidate f. Here I choose a f value that is a little below the actual fundamental frequency of this example. And now we look at the different multiples of this frequency, and we estimate, we look at the amplitude of the spectrum for each of those, and we sum all together. And we see that because it's a little before the actual f0, then the summation gives a value that is lower than if we take now the frequency that is exactly on that f0 of this example. Now that is quite kind of synchronized, we get higher value for the whole summation. And so if you take the highest of those values for all possible f, we see that we get this one. So this is one way of detecting f0. It works well here, but for instance, if we look at this, we have two pitches here because we have lower octave with low amplitude and higher octave with higher amplitude. And in this case, if we compute, for instance, the harmonic summation for this frequency at the lower octave, we get a higher value for the whole summation than if we look at the higher octave, because the higher octave is just a subset of the harmonics. You see, this is lower value for you look at the summation, it's lower value than this. So then I suggest a new improvement of this method. The idea is that actually when you look at the contribution of each different harmonic, you shouldn't look at the harmonic individually. This is not the harmonic itself that if it gets higher, the f0 is more easier to perceive. It's when you look at successive harmonic. If you have two successive harmonics that gets higher, then you perceive more easily the f0. So this is a model, I can't go into detail, but in this case, for the same example, you have this series of values that is lower for f here, for this lower octave, and for the higher octave, you have higher values. I have to go quickly, I have to switch this. And another issue, a last issue, is the previous state-of-the-art methods. They look at each instant of music, and for each instant, they try to detect the different f0s without looking at the previous and next frames. So they look at the spectrum on each successive column of the spectrum. What I suggest is to define a kind of note per set, so it's more cognitively, it makes more sense and it's more efficient computationally. And for instance, this example where you have one note here and another note like in the octave, among other notes here, but I just focus on this. And I could say, to detect this particular note, we see that we have an increase of energy over time for these particular partials. And we detect this at some point, and we create a note percept. So in other words, in the previous state of the art, for each successive instant, we detect f0s and try to detect which are the actual f0s. Whereas in the current new model, the detection is detecting f0s is identical to detecting start of notes and observing the temporal evolution of harmonics. So last to discuss, how could music perception cognition help improving the computational models? For instance, would there be new research that will help improving the models? I would be very interested to hear about this. And could these new models that we develop in the computational side be helpful for perceptive cognitive research? So your contribution could help for the open source development of our tools. And let's continue the discussion also in the forum in Moodle or in the YouTube stream. Thank you.
Yes, thank you very much for this interesting talk. Are there any questions from the audience? Yes, please.
Take this back.
Hi, so thank you for the talk. when do you, so in the new representation that you're showing, so would it be possible from an even more engineering approach, so to try to use machine learning methods to try to learn just the representation of the pitch? So in this case, so probably against all the cognitive approaches. So would it be that just a purely machine learning representation of, so not of the spectrogram, but so to learn an internal representation of pitch that is not related to these frequencies, so these spectrograms, could that solve any of the problems, or so would going the way of trying to have a representation that is more cognitively plausible be better?
Maybe it could be possible at some stage of this model to improve the model using machine learning, or maybe a large part of the model to use machine learning as a kind of way to improve that. Yeah, that's an important question. Actually,
so because of
yeah.
also a lot of these representations based on spectrograms, so then one of the issues is how do you compute the spectrogram, so then there are very many ways, and some of them are more cognitively plausible, and so the idea would be, so if there would be machine learning or an entirely new so a cognitively plausible way of representing this distribution of frequencies.
Yes. Then the question is, we have to make sure that in the training you get examples that's a sufficient range of examples that cover the kind of pitch perception that human is able to do. And sometimes for complex type of music, like back to this fiddle music or more complex, then you will need to train with examples where you will provide the transcription, the transcription. That's what the issue why I was considering that machine learning could be a limitation in those cases, but this has to be thought about, and we could try to think about it.
So, any other questions? So may I also ask you one question?
Yes.
You were talking about the extraction of the missing fundamental frequency. And in psychoacoustics, as far as I know, there are different models. So there has been this learning-based model saying that the harmonic structure is learned by listening again and again, for instance, to speech vowels. Or there are models based on time, so on the extraction of the temporal structure of the fundamental frequency in terms of the neural firing patterns of the auditory nerve. And which model do you prefer?
So that's where my expertise in cognition is quite limited, and that's where discussion, and I could learn a lot about these models. So I guess I should.
Because we're talking about autocorrelation, and that would require a temporal encoding of the of zero information in the acoustical signal.
Yeah.
And in fact, there is evidence for this encoding, but the big question is it used for the extraction of the missing fundamental or the fundamental frequency?
The fundamental frequency. Yeah. Okay, I see.
So you know. Okay. So thank you very much. And I would like to finish this session. We do not have a third talk here in this session, so you're free to go to other applications. Thank you very much.
Yeah, it's really interesting questions. I could discuss. You could give me links.
So I was asking you because I've been working on that for many years, and I was very interested in this question of